So good afternoon, ladies and gentlemen, and welcome to this webinar, Assessing the Impact of Automated Vehicles. My name is Suzanne Hoadley, and I work for POLIS, which is the network of city and regional authorities promoting innovative and sustainable transport solutions. So I've been following automated vehicle developments now for close to 10 years, mainly in the context of European research and innovation projects. But also I've had many conversations with POLIS members, so city and regional authorities, about automated vehicles, you know, talking about, well, what are their views, what do they know about automated vehicle developments, where do they see opportunity, where do they see threat, and you know, what could be the impacts. And this is something, you know, that they're very keen on understanding, is what could be the impacts of automated vehicles in terms of their mobility systems and the sustainable mobility policies that they're you know, striving to achieve. And that's where we have the LEVITATE and the CoEXist project, which are going to be presented today, which are really helping us helping cities by providing knowledge and tools to help them understand what could be the potential impacts of automated vehicles and what sort of policies they should be implementing to really capture the benefits and mitigate some of the negative effects. So this seminar is brought to you by POLIS as part of the Mobilising Mobility webinar series, so otherwise known as MoMob. Which is about turning innovation into action. We've been running these webinars twice a week since September, and they will continue through to November. And on the screen, you can see you have a snapshot of the other webinars that we are running, and they cross the broad spectrum of transport topics. And if you're interested in attending any of those, they are open to all, so you just visit our website to find more information. The next webinar will actually be on next Tuesday, and that's to do with neighbourhood planning. And there we will have 4 projects presenting, sharing their experiences. And if you're interested in POLIS webinars, you might be interested to know that our annual event, so which is really the highlight of the POLIS calendar, is going online as well. So it will take place from the 30th of November until the 3rd of December. And there are a couple of sessions about automated vehicles. So you can find more information about that on our website. So coming to this webinar, a few house rules. So the meeting is being recorded, and that recording will be sent to you. I invite all speakers to keep their microphone muted when they're not speaking. And to everyone, if you have any questions while the presentations are running, you can enter them into the Q&A box. The way we're going to run the webinar today is we're going to have 2 presentations, 15-20 minutes max each, and then we'll have them back to back, and then we'll take questions and discussion at the end. So we should have about 15 minutes towards the end of this webinar. So yeah, we're very happy to have you with us here today, and we look forward to your questions and a bit of discussion towards the end. But you can also engage with us in other ways, so with the LEVITATE project, CoEXist project, or with POLIS via the social media sites or the websites. So moving on to our speakers, so we have the first project to be presented will be the CoEXist project, which will be presented by Dr. Johan Olstam from the Swedish National Road and Transport Research Institute. And then representing the LEVITATE project, we have 2 speakers, so Professor Andrew Morris and Dr. Hitesh Bhogani from Loughborough University in the UK, which are the project coordinators. So now I will hand over to Johan. You can take presenter rights.
Now I'm unmuted also.
Yes.
Thank you, Susan. And you see the screen. We're all set. Good. So my name is Johan Olstam, and I'm normally I present myself as being from VTI. Susan already said a very, very long name. So thanks for inviting to present a little bit from the CoEXist project. which was focusing on enabling automation-ready transport planning. So we had three main pillars in the CoEXist project we'll come to, but the project ended in April. And was running for 3 years. So the aim was to prepare cities for this transition phase and to build capacity of these urban road authorities to plan for this transition from no automated vehicles to maybe 100% automated vehicles. So there were several partners, both consultants and universities and OEMs involved, and there were also 4 cities: Gothenburg, Milton Keynes, Helmut, and Stuttgart. And there were 3 pillars in this project. The first one was really on trying to make the transport models that used today by cities and consultants to make them automation ready. This was in the area when HD ready TVs were very popular. So automation ready was kind of a term that we used, meaning that we need to make the transport model of today able to be used to assess the impacts when automated vehicles is part of the traffic system. On the other hand, then we need also to apply these models in a systematic way in order to assess whether the current road design or road infrastructure is automation ready. And we do that by applying these developed models on real cases in real cities. And we also worked with developing action plans for the cities. This I will not talk about today, but that was also part of the project of looking on the traffic strategies by the cities. So how do we manage to get automation-ready transport modeling and how to use that in order to assess if the current road designs or infrastructure is ready for automated vehicles? So the first thing we struck to and need to deal with is how to model automated vehicles in traffic models or traffic simulation models. And the first question, of course, what is an automated vehicle? It's not only one thing, probably. How do it behave? And are all types of automated vehicles the same? These are questions that one needs to deal with in order to be able to do this kind of traffic simulation modeling. And of course, we have these SAE levels of automation. Most of you have heard about it. So it's ranging from no automation to full automation. But they mainly describe to what extent the vehicle can drive itself and where it can drive itself and who's responsible for the drive. It doesn't say that much on how the vehicles actually will behave, which we need in order to model them in a traffic simulation model. So in the CoEXist approach, we were actually in the call from the European Union, and the focus was really on when an automated driving system is in control of the vehicle. So meaning level 4 or 5, or potentially also level 3 when the driver's automated driving system is responsible for the drive. So we have taken an approach where we say that, okay, we look on when either the vehicles are manual driven or it's driven by an automated driving system, and then the automated driving system is responsible for operation, meaning that it has to comply with the traffic rules and regulation and comply with speed limit. I know from American colleagues that they might have a different view on that, but I think that's quite applicable for most of the European countries. So the challenge is, of course, that we try to model something that's not really there yet. There are some tries around and test cases, but we for sure don't have any data on the future automated vehicles that comes. And at least our beliefs was that the transition towards full automation will be for a couple of decades. So we'll need to handle some kind of evolution of automated vehicles over time. So we have large uncertainties related to how these automated vehicles will behave, how this technology will evolve, and the penetration rate will evolve. We also have uncertainties related to how other road users, other vehicle drivers or non-motorized road users will respond to automated vehicles. Will they change their behavior? And the travelers driving or riding an automated vehicle, where they traveler behavior adapt. So for example, will they have different perceptions of travel time? So in order to deal with this, we thought about this transition period in terms of 3 different states. Of course, one could have divided into several more states, but we thought about it to simplify into, first we have a kind of introductory stage, then the established stage, and in the later prevalent stage. And so instead of terms of years in the future, the states were defined by how common automated vehicles are, how capable they are of driving in different situations, and also how advanced driving behavior they can apply. And for the driving behavior, we developed a set of driving logics that should try to describe the full range of potential different driving behaviors these automated vehicles could have, ranging from this kind of rail-safe logic where you follow a predefined path and stops anytime you have a problems or have something in collision course. So kind of automated minibuses we see tested around. Cautious driving logic, where a vehicle that could make lane changes and not need to follow a predefined path, but would require a brick wall stop distance criteria. So it will require a large gap in order to be safe and not cause an accident. A normal driving logic, which is similar to an average human driver, but with maybe better perception or quicker reaction time, but it could also be not being able to see further ahead or anticipate what will happen as an experienced driver could. And the last one we called all-knowing, which might be an utopia, but perfect perception and anticipation of other road users' actions. And the idea with this driving logic was to capture a wide range of potential different behaviors that this automated vehicle could have. In order to put this into context, to be able to look into the evolution of automated vehicles over this transition period, we also defined 3 different types of AV classes. I will come back to why we need also the AV classes and not enough with the driving logics. But the AV classes, we sometimes I say first, second, and third generation, but in principle, the first basic AV is able to drive in one directional traffic where there's no pedestrians and bikes and non-connected road users, and then intermediate could manage structured traffic and advanced most types of environments. And all of them, of course, need to prioritize safety, but the more advanced can able to drive safe and more offensive than the less advanced. And again, of course, we assume then everyone followed the road code. And the idea is then that there is kind of evolution. So the first type of automated vehicles, they can only manage one directional traffic, and they need to be very careful, cautious driving, and maybe the human needs to drive in a more complex urban street shared space. And then there's an assumption here on that the more advanced automated vehicles at the intermediate and the advanced can manage more road environments and with more advanced driving logics. This is of course assumptions, and one could put assumptions in a different way, but the idea here was to put up a framework where you can look on different plausible directions during this transition period. So for example, here is that if you think about the introductory stage being overall AV penetration rates on 10 to 40%, for example, then we would assume that most of the AVs are basic AVs that needs to drive cautious in motorways and arterials and cannot manage urban streets and share space and so on. And the established stage, when you get more or less equal amount of manual driven vehicles as automated vehicles, then there could be a wide range of mixes because it's really uncertain on how quick you will get to the more advanced ones. And then the prevalent stage where it's mainly automated vehicles, one could maybe assume that there are more advanced AVs there and no basic lefts. And of course, one could do simulations of all potential combination of this, and then you get a huge number of combinations. So that here is also an idea of trying to reduce the number of cases and remove those that seems to be less plausible. So these driving logics, of course, it's not enough to describe them conceptually as I've done so far. So we needed to implement them in some traffic models. And this was done in the VISIM and VISUM, since PTV was part of the project. And except this framework and this conceptual driving logics, there were some data collection going on in Helmond. There were also some co-simulation with control logics from the French Research Institute VEDICOM, which were then connected to VISIM to run some co-simulations. And this was then fed into VISIM in terms of adding some new features, but also on changing parameter values for automated vehicles for these 4 different driving logics in relation to human-driven vehicles. And this VISIM was then used to run a set of simulations for common road facilities in order to calculate capacity effects and so-called personal car units, which was then used in the macroscopic model of VISUM, which is a network model looking on route choice and mode choice on a network level. And when these models were developed, they were then applied to 8 different use cases in 4 European cities. So we, as I said, we have these 4 cities, Gothenburg, Milton Keynes, Helmond, and Stuttgart on board on the project. And for each city, there were also support partners involved. So we, at VTI, for example, helping Gothenburg out, and in Milton Keynes was Cambridge, and in Stuttgart was the University of Stuttgart. In Helmond was actually the municipality itself that did the work. And there were several different types. There were not the same kind of situation in all of this. So in Gothenburg, we looked on shared spaces, and then what will happen during long-term construction. If you look on a network level, in Helmond, they looked on a signalized intersection, and then also on motorway that turns into a signalized arterial. Milton Keynes looked also on waiting and drop-off areas if you close the city for the inner city for traffic, and also roundabouts. And Stuttgart looks on network effects on the region, and also in a case with 100% automated vehicles, how could that look if you have car and ride sharing services? So of course I cannot present all the results from all of this, but I tried to summarize some of the common results that we got from applying the models. So if we look on those cases where we look on one road facility, so one signalized intersection or one roundabout, one motorway or one shared space, the general results are that in the introductory stage with low penetration rate but mainly cautious AVs, you have a decreased traffic performance. The magnitude varies a little bit. So in the you get quite a large decrease in shared space and this kind of less structured traffic environments, also in the roundabouts in Milton Keynes, while in the more structured traffic environments like the motorway and signalized intersection, this is a decrease, but it's not as high as in the other cases. And as you get more and more advanced AVs, you can then reduce the negative effects, and in several cases you can also amplify positive effects by, for example, that if you get better capacity in the traffic signal, then you can redistribute this increased capacity to the active modes, giving more green time, for example, to bicyclists. But it's more difficult to find any measures to reduce the negative effects during the introductory stage, at least among the measures that we tested. So if the AVs are this cautious, then it will have a negative impact on capacity and delay in single road facilities. If we look on network level, as I said, we had some cases where we looked in Gothenburg, for example, for the whole Gothenburg city, and in Stuttgart, we looked on Stuttgart region. We could see similar trends, so decreased traffic performance on single roads in the introduction stage, and then we can look in overall improved traffic performance in the network in established and prevalent stages. In Stuttgart, they also looked into what will happen if we start to change the travel time perception, meaning that maybe we don't value travel time as much if we can do something else when we are riding our automated vehicle. And this leads then to shift towards car and longer trips in general. And they also looked on this driverless car and ride sharing service, either as a private service or really integrated with a public transport. And direct ride sharing services achieve the highest modal share. So there's a potential. And I think this slide is quite interesting to think about, that if we start to get the more advanced AVs and better cars, and maybe even if we get more car sharing, the car will be more attractive and it will attract traffic from the public transport. That's one of the results from the Stuttgart case. But on the other hand, if we have these better cars, meaning improved capacity, and we also combine that with more ride sharing and integrated with a better public transport, we can get a modal shift towards public transport instead, and then decrease the car traffic. So it's interesting in that sense that we get the decrease in traffic performance due to cautious automated vehicles, but this decreased traffic performance lead to a modal shift towards public transport because car traffic becomes less attractive. And when we get more advanced automated vehicles and can get increased traffic performance in that sense with better capacity, we get the modal shift towards cars instead. So it's also, of course, what you do with this increased traffic performance of single road facilities. In the end, it's important. And from the measures we looked into on how to reduce the negative traffic impacts in the introductory stage, more or less the only one that seems to be useful is to say AVs are only allowed in the highly structured traffic environments because they will cause too much delay in the less structured environments. Whether that's a problem or not, of course, that's up to municipalities and decision makers, because that AVs keep the speed limit and drive more cautious could also be positive from a safety point of view, even if the traffic performance decrease. And one thing that I would like to end with is that our results from applying this for these different use cases emphasize really that it's important to do careful modeling, taking uncertainty into account when we're planning infrastructure that will likely be there for the whole area of the coexistence of conventional automated vehicles. So we really need to take potential different future with different types of automated vehicles into account when we do traffic planning of infrastructure that will be during this period. So that's all from me. If you would like to learn more, the CoEXist homepage is still there. All the deliverables are there. I'm happy to answer questions in the Q&A, or if someone would like to discuss more, then I'm of course also available for this bilateral discussions.
Okay, thank you very much, Johan, and thank you for sticking to time. You even had 1 minute left, so thank you very much. That's great. So yeah, this has been a really great project. Why do I like it? Because it's one of the few projects that I'm aware of that's really trying to deal with this transitional phase. I mean, a lot of people admit that this transitional phase is going to be difficult, it's going to be messy, it's going to be challenging. But this is one of the first projects, as I said, that I'm aware of that's really tried to give us some tools to help plan for that and to get the best outcome possible. And I love your conclusion about, you know, even if we have reduced traffic performance, we should look at that as something positive, because it might encourage people people in their car to move to other sustainable modes. And I have a confession to make, that people working in traffic management in cities over the years have said the same thing, that congestion can be a deterrent. So it can encourage people to shift modes. They would never admit that publicly, but I must confess that it has been said. So now I think we can move to our next speakers, to Andrew and to Hitesh. So if you could take the presenter, the screen, please.
Okay, good afternoon. Hopefully you can see the screen out there. So I'm just going to talk about the LEVITATE project, and I was struck by how much overlap there is between what we're doing in LEVITATE and within the CoEXist project, and that's probably something we can come back to in the Q&A session. But just to say that we're going to divide this presentation into two parts. So I'm going to give a brief introduction and overview of LEVITATE, and then hand over to my colleague, Dr. Hitesh Bhagani, who's going to take more of a deep dive into some of the technical aspects of the project, and more specifically, our work on the individual use cases, which Johan referred to as well, which examine likely changes in things like passenger car use as we progress towards the era of connected and autonomous vehicles. So first of all, some information about LEVITATE. LEVITATE stands for Societal Level Impacts of Connected and Automated Vehicles. And the overall intention of the project is to build tools to help European cities, regions, and national governments prepare for a future with increasing levels of automated vehicles and passenger cars, together with urban transport services and urban logistics. The project is received €6.4 million funding provided by the European Commission within the Horizon 2020 framework. And the project, which is led by ourselves at Loughborough University, brings together 12 partners from 10 countries, including a range of renowned research institutes, local authorities, and some global partners as well. It's a 3-year project, and it started in December 2018. As I said before, the project involves 12 partners in total. The partnership are there to address a combination of technical, stakeholder, and implementation challenges, which are involved in preparing a policy support tool for helping the decision-making process. The team aims to combine all of the necessary competences and expertise in order to carry out the technology development and ensure a successful dissemination, exploitation of project results, and to successfully launch the policy support tool to be used by policymakers at the end of the project. We have a specific work plan within LEVITATE. This sort of demonstrates what it's about. There are a number of work packages, which I'll briefly describe to you. So work package 1 deals with project management. Here we deal with responsibility for liaison with the Commission, contractual issues, etc. The bulk of the work is done in work packages 2 through till 7. Work package 2 deals with the consultation and dissemination in terms of gathering views from stakeholders through workshops, online tools and other methods, and eventually the dissemination activity, which will involve a final conference at the end of the project. Within work package 3, we have impact assessment methodologies. So we'll develop an integrated set of methodologies for assessing the impact of autonomous vehicles within the range of use cases that we'll talk about in due course. Work package 4 deals with the scenario and indicator development involving the specification of scenarios on the basis of stakeholder inputs and quantification of impact dimensions and indicators, and also development of micro simulation models. And then we come on to what are really the key, I would say, are the key work packages within the project. This is where we take a deep dive into the use cases. In work package 5, we have use case 1, which deals with automated urban transport. And here we're conducting assessments, impact assessments and case studies for automated urban transport scenarios. In work package 6, which Hitesh will describe in due course, we're going to discuss in more detail impact assessments and case studies for passenger car scenarios. And then finally, work package 7 deals with freight transport and logistics. And here we'll be conducting impact assessments and case studies for freight vehicle and logistics situations. And then finally, we'll wrap all that up within a toolkit where we'll implement the results and establish what we call the policy support tool and populate that with methodologies, case studies, and impact assessments. Much of the work to date has really been involved in consideration of the likely use cases and looking at the predicted changes that are likely to occur as the use case progresses from theory or concept through to actualization. For example, using both traffic microsimulation and mesoscopic simulation, we've been assessing the likely changes to parameters such as journey or travel time, congestion, traffic conflicts, emissions, and the amount of travel people are likely to be involved in. And as you can see here, perhaps, different approaches have been deemed necessary depending on the specific use case. So for example, with safety, we've been considering likely changes in the number of injury accidents and changes in crash types and casualty severities. For some of the impacts, we've had to use a mixed method approach, whereas for others, we've adopted a singular approach. So it very much depends on the use case as to the different methodologies that we've applied. This is the proposed operational model of the policy support tool when it becomes available at the end of the project. And it looks quite complicated, but it's relatively simplistic. Essentially, the policy support tool is based on a number of use cases and sub-use cases, which, as we saw previously, study and predict how different scenarios of use of connected and autonomous vehicles are likely to develop in the years ahead, using a number of different approaches, including the microsimulation and mesoscopic simulation modeling, together with things like system dynamics, operational research, and Delphi methods. And users of the policy support tool will be able to assess the impact of particular parameters, say, for example, congestion, based on changes that are likely to take place as automation becomes much more prevalent. And the idea is that this will allow policymakers to study how congestion in inner city areas might change on different roadways if the composition of the vehicle fleet changes as a result of the change in the uptake of autonomous vehicles. And this could include factors such as dedicated lanes for autonomous vehicles, fewer vehicles, etc. For a more detailed look at specific use case, I'm now going to hand over to Hitesh to present our work looking at passenger car use.
Thank you, Andrew, for such an elaborate and clear introduction to the LEVITATE project. Please allow me to introduce work package 6, which is mainly dealing with passenger car use case, where we are assessing impacts on safety, mobility, environment, economy, and society at a short, medium, and long-term time frame. And really, within this work package, we have several objectives to meet the aim. And we went through defining passenger car sub-use cases and identifying methods appropriate to forecast those impacts and basically operationalize those to produce impacts. And some of those impacts I'm able to share with you today. So within the work package time frame, here what you can see on the top timeline here is the LEVITATE time frame, where work package 6 alongside work package 5 and 7, which is about urban transport and freight transport. Similarly, work package 6 about passenger car use case is also sitting almost in the middle of the work and covers almost the entire period of the project. We are more than halfway through the project, through the work package, so we have more results available for some of the sub-use cases. and we'll see them in detail. Our deliverables are not due until the end of May next year. However, we are disseminating as much as we can as we have information available. So within this work package, we have several sub-use cases, and these are basically comprising of technological or policy type interventions. As you can see here, road use pricing is kind of a family of intervention where interventions related to empty kilometer pricing and tolls, various types of tolls on vehicles can be applied in order to manage the traffic and congestion, and of course influence transport modes. In terms of influencing transport mode as well, we have automated ride sharing appearing as we have autonomous cars coming into the market. So this is something we have also considered here. Alongside the road use pricing, one can imagine changes to parking availability. And here, as you can see, we can influence parking availability or attractiveness to parking by changing the parking price, or providing or replacing on-street parking with other kind of uses, such as public space, driving lanes, or pick-up and drop-off parking. In terms of managing AV traffic as well, we have also considered dedicated lanes, providing dedicated lanes for AVs on urban highways. And of course, there is a technological intervention as well that traffic engineers and controllers and authorities have, is about implementing GLOSA, green light optimized, green light optimal speed advisory type intervention. So we are looking to investigate all of them. And in particular today, I will be showing you results for these two: parking price and dedicated AV lanes sub-use cases. So like Johan mentioned in CoEXist project, they also face challenges about simulating AVs in computer simulations. And so it's really about how they behave and so on. And here in our project Levitate as well, we have faced similar questions. And the way we are addressing them is to say, okay, we have first generation and second generation AVs. And there are really some parameters within micro simulation software where we are distinguishing them from human driven vehicles to autonomous vehicles, but cautious vehicles. And autonomous vehicles, which you can see them here as aggressive, but they are basically like confident vehicles, which are able to maintain very small headway and tighter control on speed. There's also issues about unknown behavior of human, whether they will adopt passenger cars or different modes of transport, and what would be the right answer is basically a question to all researchers. So here what we have adopted is to assume some kind of choice behavior, and we have turned them into input that user can select. So by those behaviors, what I can show you here in one of our sub-use cases, what I mean by those human behavior, is basically when we think about a city center, here shown by a circle, we have some parking spaces available. So in our current scenario, in our current age, we can see that we are able to enter into the city and park our cars, our vehicles, into the parking lots or on-street parking area. And this is basically the kind of scenario that, that depicts that. We are also in autonomous vehicles era. We can assume that a vehicle comes into the city center or nearby there, drops off the person, the passenger, and then returns back empty. And similarly, we can allow vehicle to enter into the city and then force them to park outside the city center, which may be closer to in comparison to their origin. But really the parking places are placed outside the city center area. And of course, without any intervention, there is always possibility of highly automated vehicles to drive around without any passengers. And this has been speculated by many researchers and communities. And of course, we can allow vehicles to drop off passenger and return to origin, but this time origin is inside the city center. So this really is similar to the second one that I'm showing here. So between these behaviors, we can say, let's assume that we have few different types of probabilities of these behaviors which are predominant in a city, and how when they are predominant, what are kind of the impacts that we see within the city. And here I'm only showing you the traffic related impacts. And so as you can see here, we have taken Santander network supplied to us by Aimson. And also we have simulated this network in Aimson software provided by Aimson as well, one of our project partner. So as you can see by the results of delay and amount of travel, it might be no surprise that the delay is continuously decreasing as penetration of AVs are increasing. And this is mainly to do with increase in capacity. Similarly, we have amount of travel increasing because we have increasing capacity. And emissions are dropping here, as you can see, PM10 emissions, particulate matter, which is mainly due to our assumption that all AVs will be electric vehicles, mainly because electric vehicles will arrive sooner than autonomous vehicles. So as we can see in case 1, 2, and 3, where case 1 is balanced scenario, we have first increase in delay, and this is due to cautious vehicles being prevalent, and that they are making they are building up congestion, as Johan mentioned. They found in their project results as well. But as we have more aggressive AVs coming into the market, we have drop in delay, and you can see similar effects on mirrored by amount of travel. So really here we can see different types of impact, different behaviors influencing different impacts. As I show you another sub-use case that we have simulated as well, about the dedicated AV lanes. Here we have hypothesized that the baseline scenario is where we don't provide any dedicated lane. And the idea behind that is basically to, providing dedicated lane is basically supporting the idea that by segregating traffic, AV traffic in one lane and not allow other human traffic in different lanes, we can increase safety. So there is less interaction between AVs and human-driven vehicles. So there are different options here. we can provide AVs, AV dedicated lane on motorway, either innermost or outermost. And of course, in the UK, we have A-type roads, which can be considered as an urban express road as well. And we can also provide, well, we can see whether any dynamic control will have any effect on the impacts. So for this sub-use case, we considered Manchester network, and also supported by Aimson. And as you can see by the results, the conclusions are similar here, similar to the previous sub-use case, that the delay and amount of delay is decreasing and amount of travel is increasing. However, the interesting contrast we find is that providing dedicated lane on motorway as well as A road has significant more increase in delay compared to AV's dedicated lanes only on motorways. So really here, the discussion points that we can raise here is that the driving around, if that behavior is prevalent, we can start seeing more congestion and more delays in the city center area. And in terms of dedicated lanes, we could benefit more by having them on motorway in comparison to urban settings. And of course, by using these type of results, authorities can navigate through different policies and make those changes at the time where they think would be most effective. So rather than having those policies very early on, they might switch them on maybe at 30% or 40% arrival of AVs, market penetration. So this is all from LEVITATE. So thank you very much for listening to us. And I would like to acknowledge European Union's Horizon 2020 for the funding, and of course, all partners within the project for providing the various input. So thank you very much.
Thank you, Hitesh, and thank you, Andrew, for taking us through that. So, as Hitesh said, this is still very much work in progress, and there will be more findings from the sub-use cases. You know, watch this space over the coming 12 months or so. So now we can open up for questions. We don't have any questions in the Q&A box for the time being, so please don't be shy. Please enter your questions. But I think for the moment, Johan has a question for Hitesh.
Yeah, thanks. It's actually interesting. I just wonder when, just a clarification for the dedicated lanes, was they only that there were only AV lanes, or was it also implying that the AVs need to drive in those? So there were dedicated lanes both for AVs and conventional vehicles, or was it the AVs could drive in any lane they like?
No, we provided AV lane, but those lanes were basically shared by taxis and buses as well for A road, which is where you expect to have them, you know, shared kind of lane for buses and so on, at least in the UK. So we didn't make them exclusively AV lane only for A roads. But for motorway, we didn't make them compulsory for AVs, but we didn't open them up for human-driven vehicles.
Okay. Yeah. So the automated vehicle could use all the lanes. Yeah.
Yes, correct.
Okay, Hitesh, can you, and while we're talking about the sub-use cases, can you explain how you arrived at this list of sub-use cases?
Yeah, certainly. Interesting question. So within the project, at early on, before during the early stages of work package 6, certainly. We had a workshop arranged at Gothenburg, if I can remember correctly. Yeah, that's where we engaged with stakeholders who are involved with policy making, strategic decision making, and so on. Regional authorities, city planners, traffic engineers, traffic controllers, and so on. The list goes on, basically. But basically, we engaged with stakeholders. We had discussions about what to expect in the future, and what can be done in order to harness benefit from AVs. And this is where we kind of gathered ideas about the sub-use cases that can be investigated. And these are the sub-use cases that basically filtered through the city's needs.
Yeah.
So that's
thank you. So just to maybe reinforce what you've said, is that we have a strong involvement of different stakeholders within the stakeholder group of LEVITATE, in particular city authorities and regional authorities as well, and I believe one or two in the audience today. And I think strong city involvement was an important feature of the CoEXist project as well. I mean, they were the ones, I don't know if you mentioned that, Johan, but it was actually the cities who actually defined the use cases, which made it very challenging for the other partners to implement. But the questions are starting to come in now, so maybe we can switch to those. So the first question from Matti is, do you think you can really define AV behaviour? Can you define it very well? So I don't know who wants to take that. Maybe Johan first.
I guess in some sense, if you think about that, we suggested 4 different types. That's kind of an answer to this question, saying that no, probably not. So you need to consider a wide range of potential behaviors, especially since I don't think you can define it for future automated vehicles that we don't really know. And I think the feeling from CoEXist is also that, okay, the OEMs maybe can tell us something about how their first or their prototypes would behave, but they will not, because it's proprietary information. But even though they will have difficulty to tell how will the future ones behave, and even more proprietary, probably.
Okay.
Yeah, I agree with that. I think the problem is we can probably predict how the technology is going to behave, because technology is reasonably predictable. But we can't. What we can't do is predict how people are going to use the technology. And as the technology develops and things become more clever with artificial intelligence and machine learning, then our predictions are more likely to stray from what is reality.
Okay, thank you. And I guess the environment, the road environment, is an added complexity, because the way a technology behaves and a user interacts with that technology, again, that depends on the environment that you're in. I mean, and that goes back to the very nice table that Johan showed, which shows that a vehicle of a given automation level will behave differently depending on the road that it's on, whether it's in the middle of an urban area with lots of pedestrians, cyclists, parked vehicles, public transport vehicles, on a rural road or on a motorway, it will behave differently. So I guess that's an added complexity. Okay, so we had one question for Hitesh about parking use case. Do you want to answer that, Hitesh? I think you've answered it in writing as well. So the question was, does the parking use case involve the possibility of parking outside the city, meaning that AVs driving empty runs during pickup and drop out phases, or rather, what is the measured distance between parking areas and city centre? Quite a long question.
So if I can answer the first part, we did provide parking space outside, just outside the city city area, inner city ring. That was shown on the slide. So yes, the the AVs would have choices to go back to origin or park in a nearby area. And so the parking was provided outside the city center, yes. So they would go and park in the outside. But those trips who originate from inside the city center, they would have possibility to go back to origin in the case where we remove all parkings within the inner city. Yeah. Well, I hope that's clear enough.
Okay, thank you. So maybe a question for Johan, because CoEXist is finished. It finished about 4 or 5 months ago. Some very interesting results, especially the use case findings, and you can get them on the CoEXist website. But based on the findings of and the work that you did in CoEXist, what additional research needs to be done, or were there gaps revealed by CoEXist, or things that you weren't able to address efficiently? I mean, what recommendations would you have for future research? And this question is very timely because probably you're aware that a new European research partnership on CCAM is being proposed under Horizon Europe, so the successor to Horizon 2020. So there's a lot of work going on at the moment to set up this partnership and identify, you know, some of the strategic research priorities in the future.
Yes, I guess it's worth starting to say that, okay, CoEXist really focused on traffic performance impacts, and as I understand, Levitate is focusing on wider impacts. So that's of course one of the things that need. But if we focus on the traffic performance impacts, I mean, the aim here was really to take the tools that are used today in transport planning, trying to make as good as possible given those. Of course, this limits also the possibilities on capturing all different aspects that one maybe need to capture when modeling automated vehicles. So I think parts that need to be further investigated and thought about from the traffic model point of view, especially from microscopic, is how is the perception handled. So it might be from sensors of the automated vehicles, but also connectivity. But commonly there's maybe assumed that there's this information just at hand, there's no delay for automated vehicles, and there are no errors or total accuracy. And so this kind of things might be important. And I think also that as soon as we get more and more information on how this first type of automated vehicles behave, then of course this need to be taken into account. Also investigating several different types of road facilities from a wide range. We were, as you said, the cities here decided on the use cases, and we had to apply for that. There's pros and cons on this, but I mean, it could be quite useful to try to make a systematic assessment with a wide range of different driving behaviors for common road facilities in different countries and different cities. I don't know if that's actually done now in Levitate or not, or if it's also as in CoEXist that you can do one sub case at one place, and then the budget is limited in that sense. So I think there's, on the modeling side, there's some need to further develop, and of course on when you go to the network effects and effects on travel time perception and mode choice and so on, then things gets even more complicated. But you need to start on the micro scale in order to get how is delay, travel time, and capacity affected, in order to at least have that as input on when looking on the mode choice and route choice.
Okay, thank you. I think in Levitate we're not running the same use cases in different cities. We're not doing that comparative analysis either, because there are so many sub use cases. I think we have quite a lot. Yeah. Is that right? Yeah. Yeah.
So you have to choose either variety of use cases or kind of quantitative or replications of the same use case. And of course, to sell to European Commission, then variety might be more important than, but as a researcher, you would like to study the same in several cases in order to understand if there's a differences. Yeah. But then you only get results for signalized intersection or roundabout. Yeah.
Okay, well, we're reaching the end of our session. It's already 5 o'clock. So I would just like to ask one final question to each of you. And if you could respond, say, in 15, 20 seconds. If tomorrow a city was to come to you and ask you what it should be doing to prepare for, to plan for connected and automated vehicles, I mean, what would your advice to them be? So just 15, 20 seconds, and then we can close.
Yeah, I guess the short one is just to say that, okay, apply the CoEXist assessment methodology, and then you get at least the first hint.
Similarly, use our PST.
But it's not ready yet. It won't be ready for another year or so. So, Andrew, give us something else. You can't say CoEXist or the LEVITATE method.
No, I would say use our PST as well, but I think the answer could be quite dependent on the city characteristics, because obviously the policy intervention that you use to tackle a challenge in one particular city, where you might have, for example, low cycle usage, and for example, Amsterdam is completely impractical in another city where you've got low cycle usage. Sorry, high cycle usage in Amsterdam, low cycle usage in another city. The two interventions are going to be quite different.
Okay. Okay, well, I think we will have to come to a close now. We have a few more questions on the Q&A box, so our speakers will have committed to respond to those questions, and we'll send those out by email after the event. So all that remains for me to say is, well, thank you to our speakers, thank you to our audience, and thank you to my colleagues, Balázs, Maria, and Alexia for assisting me in the organisation of this webinar. And thank you very much, and have a great evening. Thank you.
Thank you. Thank you.